And we are back for the last session of today's journey on how to move from bad GPU APIs to a different kind of GPU API, to a different kind of bad GPU API. So in the previous steps, I've shown you what is involved when we start implementing the Gray-Scott reaction on GPU. We saw that the basic Vulkan context logic can stay almost the same modulo some logging tweaks. We need new compute pipelines, obviously, because we are doing different computations. And we are going to need different memory resources to bind to those pipelines. And I attempted to show what kind of challenges get involved when we try to port CPU application to a GPU application, and how the specifics of GPU hardware will affect our abstraction design as software developers. Finally, we now have GPU programs, data. It's time to put them together and get a full working simulation. So what are we missing? One thing we are missing is a way to schedule our actual simulation steps. And that will be the job of a new function called schedule simulation, which is basically all that remains of our former huge build command buffer function once we extract everything we can and make it focused on running the simulation only. We start with yet another computation of our workgroup size. Remember, the design we have used for the simulation is that we will be spawning one GPU work item per active cell of the simulation, not including zero padding around the data set. So here we do not have the addition of the padding, but we still have a division by our workgroup size. This is GPU, we won't get around it. After this, we can bind the compute pipeline associated to your simulation. And then we will do a bunch of steps. We will basically do all the simulation steps that happen in between two output images. For each of these steps, we are going to call the update method of the concentration double buffer, which will take care of the double buffering for us, and give us each time the descriptor set that's associated to our current inputs and outputs. We will then proceed to bind this descriptor set and schedule one simulation run. One thing which is important to remember here is that at this point, we have not actually asked GPU to perform any work. We have just prepared a recipe of sorts called a command buffer, which is a list of action that the GPU will take as soon as we send it this command buffer. And here we are using a design where we assume someone before us allocated a command buffer, maybe put some commands in it, and we are going to put more commands at the end. The reason why we are using this design is that this will allow us to handle the initialization of our data set a bit more elegantly later on, as you will see. The optimization-minded among you may be shocked or hurt even by the fact that we are computing the number of workgroups every time we call this function. I can assure you that your compiler is totally able to optimize this repeated computation into only one computation. And even if it doesn't manage, compared to the cost of everything else we do, dividing a pair of integers is not the worst thing in the world. There is, however, something that I would like to point out, even if I have not yet written the course part that will go into more details on this, which is that here we are building a command buffer which can get really, really large because the size of this command buffer is dictated by a user control parameter. This can become a problem because while we are building this command buffer, our GPU is potentially doing nothing. And the longer it gets, the more likely it is that we are starving the GPU of work. So in a more realistic simulation, what we would most likely want is to have some kind of internal linearity where at some point, if we have enqueued too many commands, we send the current work we have to the GPU so that it can start working, and then we start enqueuing again. We are not doing this yet because this is version 1. We want to be as straightforward as Vulkan will allow us. Then we rework the run simulation. And here I played a bit again with software abstraction design. What I wanted here is to fix one slight defect of my CPU simulation, which is that the run simulation was part of the common library, but actually it could only be used by the simulation binary because it did things that only the simulation binary should be doing, like writing data to an SDF5 file. I wanted to address this with a slightly better abstraction design, which here takes the form of a pair of callbacks. One of these callbacks will be run after we have scheduled the simulation steps in the command buffer, and it will allow the caller to enqueue extra work in the command buffer. And this callback will also be provided with the knowledge of the current simulation input, which is the output of the previous step. And the second callback will be run after we have waited for the GPU to do the work. And by combining these two callbacks, we'll be able to schedule a download of our GPU data to the CPU in the first callback. And then later, once the data is downloaded, get the data, write it to SDF5, and update our progress bar. And now we get a better separation of concern, and everything is nicer. In terms of the rest of the code, it looks like this. So now we have GPU pipelines to set up, one for initialization, one for simulation. That's why now the struct is called pipelines. They share a common layout because this allows us to have common descriptor set, which makes everything easier. I have this small utility in there which allows me to spawn as many command buffers as I like. I will always create them in the same way. I do not need to fine-tune this. I create an initial command buffer. And in this command buffer, I will schedule the initialization of my simulation dataset. Then I will do a loop over the simulation output steps that I need to perform. So the number of images that I intend to produce and write to SDF5. In this loop, I will call my schedule simulation method, which you have seen earlier, whose goal is to enqueue all the commands needed to run the simulation steps we need to run. Then I will invoke the user-specified callback so that if the user of run simulation wants to download stuff to the CPU, for example, they can. And at this point, I consider that my command buffer is complete. So I will build it, send it to the GPU, and for now, synchronously wait for it to be finished. This could be improved later on. Once this is done, I can notify the caller that the data, if they ask for it, should be ready, and they can write it to the SDF5 file and whatever. And then, because I have used up my command buffer, I have submitted to the GPU, I will create a new one and repeat the cycle for the next loop iteration. As I mentioned, the SDF5 logic is now inside of the main simulation binary instead. What happens there is after parsing command line options, setting up a progress bar, setting up a Vulkan context, this part has not changed. I will set up a CPU buffer for download. This is now the responsibility of the main simulation binary only, since we may not want to do this in the benchmark. Then I will set up my SDF5 file output. Again, this is now the responsibility of the binary, not the library. And I will run the simulation with, as I mentioned, two callbacks that allow me to schedule my optional data download and saving to SDF5 and updating of progress bars. Once the simulation is done and I run all the steps, I will close my SDF5 file. This could be done by the destructor, the drop implementation, but doing it manually allows me to handle errors explicitly, which I would not otherwise be able to do. And finally, once I have written all my SDF5 data, I can declare that the computation is finished. This will make my progress bar disappear, and I'm happy. Beyond that, I have actually, sneakily, in the code base that you have been provided with, prepared the benchmark in such a way that it can now benchmark this version of the simulation in many different configurations, so that you can see how the performance depends on the various available tuning parameters. We could be studying this further, but benchmark runs will take a while, so if you want them, you can maybe check out the solution branch and start them. Meanwhile, I will tell you about the one optimization that I managed to implement before this course, which is an optimization that you will not be seeing in other courses because, this is a compute school. We like to focus on stuff which is compute, even if it doesn't matter to a particular use case. In this particular case, it doesn't matter because our simulation, by the time we have GPU levels of computing power available, actually is not limited by the speed at which we compute data anymore. It's limited by the speed at which we write it to disk. And this is the case even if you have fast flash storage. And there is a simple way to prove this, which is to run the simulation twice, once in its default configuration, which will put the file in your local directory, and another time sending the output to something which is a bit of a Linux hack called devshm, which is backed by RAM, so much faster. If when you run a program that performs any kind of I/O in these two configurations, you see a big performance difference, and I would call the difference between 2 minutes and 20 seconds rather big. What this means is you are bottlenecked by the speed at which you're writing data to your storage. And this is the thing you should be working on first, actually, not the simulation part, because it really doesn't matter. So how do we take care of it? We have many, many different ways. It's I/O optimization. We don't do it in this school, but it's cool. Study it. The first thing we should do is make sure we are using the fastest storage device that we have available, which meets our engineering requirements. For example, one very common mistake in HPC centers is to run programs in your home directory, which is typically backed by a distributed file system that has extremely bad I/O performance. HPC centers are aware that distributed file systems are performance challenged. They are not here for performance, they are here for consistency. The idea is that all your nodes can see the same data at a price. And so what you should do if you need a very high throughput I/O is to use something called a scratch file system, which all good computing centers have, which is basically a disk on your local machine that other nodes in the supercomputer don't have access to. And then you get much better performance. The RAM disk I showed you earlier is a cool trick when you are not too tight on RAM, which can allow you to get even faster performance in situations where you do not actually to keep the output after a simulation run, because it's going to be part of a pipeline where the next stage will take this output and do something else with it and produce the result you're actually interested in, for example. Second thing you can do, as always in hardware, if you have money, use it. Okay, not that much environment friendly, but sometimes more hardware can be the solution to the problem at hand. In particular, if you know your application is very sensitive to I/O performance and your server is using a spinning disk, it may be a good idea to have an SSD for those I/O intensive workloads. It will give you a big I/O throughput boost at almost no application costs. Then we can start storing less data. This is what the other courses have been sneakily doing. So you increase the number of simulation steps you do between two writes. So you write less images, but you do more work between images. You can make the eyes of Vincent bleed by storing lower precision data. You know, half precision, all kinds of lossy compression. People have been getting really creative with this. The point here is often the precision at which you need to store data is not the same as the precision you need during a computation. Because during a computation, you have things like accumulation, cancellation, and this sort of stuff require you to have more bits of data available than the actual precision of the inputs you are getting and the outputs you are producing. When you reach this point where I'm done with my computation, I should store the results, it's a good time to ask yourself again, how many significant digits do I expect on my results? And what is the appropriate storage type for this number of significant digits? But let's say you have an annoying physicist colleague who will not tolerate any form of lossy compression because they don't know what their precision requirements are. It's more common than you think. Then what you will do is you will turn to lossless compression. It used to be the case that algorithms like gzip were effective. That was on spinning disk. On modern flash storage, the storage is so fast that if you try to use some format like gzip, you will spend more time compressing your data than storing it. And it's better to use those algorithms like LZ4, LZO that do not compress very much, but compress very, very quickly at very low CPU costs. There is another optimization that you can do. Again, this optimization, by the way, I sorted in the rough decreasing order of decreasing expected effectiveness. So on the top, you have the stuff that should give you the biggest benefit. The more you get to the bottom, the more it's a cherry on the top, you know. At the bottom, so on number 6, I suggest that if you have some kind of I/O-heavy operation, but the time you spend in I/O remains relatively close to the time you spend computing stuff, it's a good idea to offload your I/O to a different thread, because this will allow you to have I/O and computation that occur in parallel, and an I/O thread that spends as much of its time as it can writing data to disk. For a few selected file formats, you can actually even do better than this and have multiple threads doing I/O at the same time, but that's not an option for many I/O libraries, so I will not get into details of this here. And finally, once you have done all that, you can start thinking about the stuff that makes sys and mins happy, like you know, tuning the block size of your writes, comparing whether HDF5 and FITS is faster. Spoiler, they have both been optimized enough. This is the small gain region, but you know, if you want to get the best of the best, we need to do that too. So here, just to put what we've done so far in perspective, what I've done above by using RAM disk is actually an example of strategy number 1. For my benchmarking purpose, maybe I don't need actually to store my outputs to a persistent non-volatile storage device. I can put it in RAM. It will be much faster. Because the spirit of this school is not to teach you all about I/O, I will show you another optimization which is easy to do, even if it's not the most effective, which is to make I/O asynchronous. And then we'll switch to the extreme version of the store less data strategy, like everyone else, where we just store no data and then everything becomes faster. So how do we actually do this asynchronous I/O thing? The general idea, at least the simplest design you can use, and most of the time it will be very effective, is to have two threads. One is in charge of handling the computation, another is in charge of handling the I/O. And in between the two threads, you will put a shared data structure, which is a queue in, first out order. The fact that it's first in, first out will allow you to get the same result as if you ran the program sequentially. One very important property of this queue is that it should be bounded. That is to say, it should accept up to a certain number of elements. And if the number of elements gets bigger than this, it should reject elements and have the calling threads block. Why do you want this? Because otherwise, in applications like what we've seen above, what will happen is your compute thread is faster than your I/O thread, so the I/O request will pile up, and your memory usage is going to explode. You don't want this. Assuming you have used a bounded FIFO queue, then you will get two scenarios. If the compute thread is faster than the I/O thread, then what will happen is, the compute thread will quickly fill up the buffer, start sleeping. At some point, the I/O thread will be done writing its current image. It will fetch the next one. This will wake up the compute thread, which will prepare another one, while the I/O thread is writing. And what you will effectively get at the end is an I/O thread that spends 100% of its time writing images continuously, because it's basically the limiting factor. Again, for this to go well, you really want to have a bounded queue. If you are interested, look up the notion of back pressure. This is a very central concept in any kind of network programming, distributed systems. And yeah, anytime you want asynchronous I/O, usually you want bounded queues. Now, let's say that we actually did not see this coming, but maybe the I/O thread now is faster than the compute thread. Maybe we are doing lots of compute. This is actually the case for CPU simulation. It's fast, but not fast enough to saturate my SSD, because SSDs are really fast as well. What will happen then is that the compute thread will be the one that's working 100% of the time, furiously pushing images through the queue as fast as it can, while the I/O thread will be fetching an image, writing it, and twiddling its thumb, waiting for the next image to arrive. I would argue that this is not a good scenario for asynchronous I/O, because we will pay a few extra costs linked to the fact that we have two threads, communication, and so on, and we will not amortize them with faster I/O because we are not actually limited by I/O. So this is a special purpose optimization. Know when to use it. In the real world, applications may not fall neatly into this dichotomy. You may have variable compute performance, variable I/O performance, which means that sometimes the I/O thread will be fetching lots of data quickly, and sometimes it will not fetch data for a while. That's typically the case if your operating system does some batching under the hood. If you are in this sort of situation, then what you will want to have is a bigger queue with more storage capacity. A larger queue will not allow your program to get faster if it's limited by the I/O device. What it will allow you is to get more tolerance to variation in compute and I/O speed. So what does it look like? Well, first, as I mentioned, the number of elements in the queue is a tuning parameter. So like all tuning parameter, we will expose it on our command line, because we are nice people. We don't do hard-coded parameters. Then we will write a function which sets up an I/O thread, which accepts images from an I/O queue, and then writes them down. And it looks like this. So first of all, we set up something called a sync channel. That's a primitive from the Rust standard library, which is basically bounded FIFO queues with some tweaks. Then we set up the AZA5 writer, because this is not going to be the responsibility of the I/O thread. We want to get this off the main thread. We are going to make a copy of this. I will get back into why we need to do that. And then we will call the standard library function called std_thread_spawn, whose purpose is to start a thread and give you back a handle called the join handle that you can later use to wait for this thread to be finished. Inside of this thread, our thread will be repeatedly getting new images from the other side of the queue, writing them down, and when it's done writing, it will increment the progress bar so that we can still see some progress. At the end, we will close the HDF5 file, say your progress bar is finished, and we are done. When we've done all this, we get two things: a join handle, which is something we can use to wait for our IO thread to be done, and a synchronous sender, which is one of the sides of the FIFO queue that we can use to push images into the IO thread. And that's all we are going to need. Now to get back to the thing, so here's the reason why I need to do this, is that this parameter comes from the option struct. And the option struct, if you look at it, is something I get by reference. And because Rust cares about memory safety, it does not let us send references to threads by default, because then we need to be careful about keeping the data that's referenced alive as long as the thread is. So what we're doing here is we are making a copy of this tiny integer, which is the only thing we care about. And we are moving this copy into the thread, and then it's an independent copy. The thread can have fun with it, and there's no risk of reference invalidation. Another thing you will notice is that my FIFO queue does not take array views as we had before. It takes owned arrays of data. The reason why that is the case is that, if you remember, our array views are borrowed from the CPU download buffer. And as soon as we are done with this buffer, the general computation logic is free to use it again to download more results. So we don't want to send our thread references to a buffer that will be overwritten later on. It won't work. So what we do instead is we are going to send owned copies of the data, which means that we can get rid of our hack in the HDF5 writer because we don't need it anymore. We have owned arrays with contiguous storage. The main function then becomes this. So we parse our command line option, set up a progress bar. We start an IO thread. Before we used to set up HDF5 here. Now we say this is a responsibility of the function that starts the IO thread. We get back a way to send tasks and a way to await the thread. Then we set up the Vulkan context as usual, the download buffer. This part has not changed. And in our second callback here, after the data has been downloaded from the GPU to the CPU, what we will do is, instead of processing it right away and writing it to HDF5, we will send an own copy of this data to the IO thread for further processing. And then here we have something nasty. This combines multiple ergonomic flow of the Rust standard library into 2 lines of code. It's those sort of lines of code that are written in pain. So we want to wait for our IO thread to be done. And the reason why we want this is otherwise we cannot handle errors that are linked to the IO thread crashing, like maybe something as panicked, for example. But here we hit the first ergonomics roadblock, which is that when we do this, we get something that does not implement the standard error trait, because panics in Rust are weird. So we need to handle this in an unusual way by crashing if the thread is crashing. Okay, that's not nice, but it's fine. And when we await the IO thread, we need to take a second precaution, which is that we need to drop the IO channel before we do that. Otherwise, what's going to happen? Let's walk back a bit into our IO thread. What it does is it waits for data coming in from the receiver. And when there is no data coming anymore, it will close the file and stop. But how does it know that there is no data coming anymore? It knows because the main thread has dropped the IO channel. So if we don't do it explicitly, we will get something called a deadlock, where the main thread is waiting for the IO thread to finish, while the IO thread is waiting for the main thread to drop the IO channel, and then nobody makes a move and your program is stuck. So yeah, couple of nastiness from the standard library that I'm not too fond of, but now you know. And what you do get at the end is about 2 times speedup. But what I find most interesting, and did not get the time to analyze, unfortunately, is that if you look at it, the user CPU time goes up. This is expected. We've created a bit more workload linked to the fact that we have 2 threads now, and we need to transfer data between them. But the system overhead, which represents the amount of time we spend in the kernel, has gone down. And this I don't have a good explanation for yet, but I will be investigating later on. Do we have questions so far? Maybe on Discord I see some stuff. Someone trying Python and having problems. Yeah, environment is hard for everyone, sorry. Yeah. Maybe, peut-être on en reparle après, pas, si c'est spécifique à ta machine. Okay. This is about machine-specific debugging, so since I only have half an hour left, I prefer to do something else with the rest of it. So now I would like to show you a bit a glimpse of what GPU,
So if you would use the other strategies you listed before, the 7 ones, would it theoretically be even faster, or?
Yes, you could get faster. I mean,
okay.
As you saw, we got a huge improvement by using a RAM disk. As I mentioned, this is great. The best storage device when you can afford it is DevNull. It's extremely fast. Yeah, faster storage. I thought I only have 1 SSD. You know, that sounds a bit pretentious when said that way. I could have a RAID of SSDs that each have much better performance than my limited laptop budget will allow. There used to be some SSDs that are basically RAM sticks on a PCI Express slot. I don't know if you can still buy them. Less data. As I mentioned, the ordering is not strict. It's just a rough idea of how much you can get in realistic situations. Obviously, less data is better. Smaller data is better up to a point where the data is meaningless because it's not precise enough.
Yeah. Okay, thank you.
How does this async I/O compare with direct storage? That's a good question. I would need to look up the direct storage part to answer this. But I put it in my to-do list for later. So maybe let me show you a bit GPU profiling on something other than NVIDIA hardware. Lets you think that only NVIDIA has nice tools. Personally, I've been burned by NVIDIA drivers one too many times, so I decided that as much as I can allow it, I would not have any NVIDIA hardware on my computer ever again. And this is a choice which had consequences, as you can imagine. But I think it was the right one.
What do you use?
AMD. If you want performance and it's not NVIDIA, it has to be AMD. Performance is not, GPU performance is not something that anyone else I know of does well.
And your CPU is not crashing?
No. You know, there are two things on AMD actually. There is the graphics stack. No, but let me show the profile first and then I will zoom. There is a graphics stack and there is a compute stack. The graphics stack is the Vulkan driver. This part is extremely stable, has been for many years, and it has even been tightly optimized by people from Valve, the authors of Steam. And then you have the compute stack, which is called Vulkan, which is one of the worst pieces of software shit that I have ever been exposed to. The nice part of doing Vulkan is that I only need to touch the good part of AMD software and not the bad part. So this is a profile of the live simulation that I have been showing you earlier, and it seems it does not support zoom, so you will need to trust me when I point things on the screen. Sorry. So what do we have? We get a set of frames, which are images that get shown by the window that I put on the screen. For each frame, I can see what the GPU has been doing. So here it's been processing a big command buffer, then a smaller command buffer. I can zoom in a bit. And then another command buffer that involves something called vkquepresent, which, if you knew about parts of the Vulkan API that I have not shown you, would tell you that this is the part that actually renders stuff in a window. So what this program does, and it's not optimal because I never got the time to optimize it properly, is it does all the simulation steps. Then it downloads the results to the CPU side, and then it uploads it again. I need to fix that at some point. I will someday. The reason why it does that is that this allows me to render data both from the CPU side and the GPU side. I can switch between all the different implementations of the grayscale simulation. So here already, if I didn't know this profiler would tell me that I have something fishy going on. But it tells me other things. It tells me this application is CPU bound. And the reason it tells me that is that you can see that the GPU is not working all the time, which from the perspective of GPU manufacturers is bad. You should be getting the GPU to work all the time, doing hopefully useful work. The reason why it's not working all the time is that, remember, we are doing 32 simulation steps per image. And as it happens, this GPU is so powerful that it can do all the 32 simulation steps in less time than a screen frame. So at some point, you've done your steps, send the image, and you are waiting for the screen to display the next image. If you paid attention earlier, this is another instance of the bounded FIFO queue pattern that I mentioned. Again, for any kind of asynchronous I/O, you will want this sort of pattern. I can get more information, like I know that in each frame I do 3 submissions to the graphics queue, which is the main queue of my GPU. And all 3 are command buffers, and I'm using 3 weight operations. I don't remember why 3, I will need to look it up. And I can look at the barriers, and I see that I have many barriers because Vulkan is not perfectly optimal in terms of how many barriers it inserts. But thankfully, that doesn't matter. Because as the profiler tells me, I'm spending 0.04% of my GPU time in API barriers, and frankly, this is not the kind of performance I care about. I can see that the most expensive event is the dispatch of a specific command buffer, and I can tell you, because I know my application, that this is the buffer that does the simulation and not the one that does the drawing. We saw that a bit in the earlier timeline. But if I didn't know, this is the place where I could check. I can see that I have 2 compute pipelines, and I can have some statistics which will tell me, if I have something like overly complicated GPU code that the GPU hardware struggles with handling, resulting in worse performance, and some system information. And then I have the event screen. And what the event screen will tell me is how one GPU frame looks like. So here I have this timeline. And at the top, I have the graphics queue, which for this GPU is the main queue that can do everything, as in OpenGL. And at the bottom, I have the asynchronous compute queue, which is something to which I could send extra jobs when there are already jobs running in the main queue. Here, I am not using this capability at the moment. Maybe I could somehow restructure the application to use this extra hardware resource. If my GPU were not a laptop GPU, but a bigger GPU, then I would also have a dedicated transfer queue, also known as DMA queue, which allows me to transfer data while other stuff is going on. And this would allow me to get even greater performance by overlapping data transfer with computations, as David mentioned. I can see that my GPU, even on the graphics queue, is not fully utilized. It's like half utilized. This is something we've been telling you over and over again now. Full HD is not enough to saturate your GPU with a grayscale computation. You need more. At least with this particular kernel, I intend to eventually implement a trick that Pierre did, which allows you to get a bit more utilization. Then you can copy back, and copying is always a lot more efficient than computing. You know, we should have a GPU programs that only made of copies. Everything is so much better from this perspective. And here you get some statistics about how we are using the various layers of caching in our GPU, you know, how effective it is, and so on. This could be used if we suspect a memory bottleneck, and we could actually tell with those statistics if we do have a memory bottleneck or not. Here you can see that our first level of level 0 cache has lots of hits, but when we go out of it, the level 1 cache is not that well utilized. Maybe there's something we could do here, but I would need to get some hardware schematics first to know what the level 0 cache corresponds to. Profilers give you info, but you need hardware specifications to know more about what the information means. I could see other things, but I will just show you a different view. So this shows you how the execution of the command buffer is decomposed into individual commands. So here you can see that we have compute dispatch commands separated by no less than 4 pipeline barriers. That's 3 too many. We need 1 because we don't want the simulation steps to overlap, as they cannot, because the result of the next step depends on those of the previous step. But yeah, Vulkan is not doing something very optimal there. That's why they are currently reworking their command buffer building process. It's not yet as good as it should be. And then you see that the final copy is a bigger thing, which is perhaps why it has better utilization. And you can look more into the statistics of each pipeline and see how well it utilizes the hardware. And you can do better than this. You can actually look at the instructions. So let me first look at the simulation shader. And here I have annotated GPU assembly, which I can study because NVIDIA, AMD has documentation for their internal assembly that I can use to see how the various instructions work. And I see how much time I expended on particular operations. And here you see that there is an image sample operation that seems particularly expensive. Maybe something I should try to improve upon. Spoiler, this is the access to the center element of the stencil. But this I know because I have looked at the GLSL source code beforehand. You see that after this, the second sampling is not perfect. It's also spending a bit of time, and then the next ones are very fast. And what's happening there is that you get all your GPU work items hitting the central location, and then they will start using the other location, and some of these locations will be in the first level cache, and so you will get fast access. But because your GPU work items are not executing at the same time, they are executing concurrently, it will take a while for all the data to have reached the cache. So the second element, you do not get perfect cache locality. We could improve upon this with manual caching using shared memory. And then after that, it does its job as you would expect. You get perfect caching. Then you get this sort of weight CNT. I have no idea what this is. I would need to look the manufacturer documentation because it looks interesting. I spent some time on it. And then at the end of the program takes a while. So this tells you that you don't want your GPU kernels to be too simple. You want them to contain enough work to amortize the cost of running a work item. So that will be it for the profiling overview. Are there any questions? If not, I will ask myself a question. Why am I showing you a profile of the live simulation and not of the code that we've been working on? Remember, earlier I told you that there is one problem with Vulkan Profiler, which is that they assume that Vulkan is for graphics, even if I have hopefully proven to you that you can use it for other things than graphics. In particular, one thing this means is that they are very tightly centered on the notion of frame that gets displayed on some surface. And this particular profiler cannot work when there are no frames displayed on any surface. And that's a shame. If anyone from AMD is listening, please fix this. It's a shame. So to be continued when I find the time to write the other optimization section, getting this, to competitive performance with the other implementations. Otherwise, it's a bit. People will be like, yeah, Rust is slow. No, Rust is not slow. It's just I spend too much time fighting with all those GPU environments, broken containers, broken drivers, broken GitLab runners that I did not have enough time left to actually write the course. That's what DevOps was supposed to save us from. It has failed. I wish it didn't. I wish those Discord screenshots were not so tiny. So where is the borrow checker? I'm happy. Borrow of move value progress. What are you doing here? Yes. So the problem here in the screenshot that Matthias is showing is that when you set up the Vulkan context, you are moving in the progress bar, which means that the Vulkan context now gets exclusive access to the progress bar, and the rest of the program doesn't have access to it anymore. That's the basic rule of moving in Rust, unless copy types are in. But here, after moving it, you're trying to use it again in this callback. And that doesn't work. In C++, it would be called use after free, or use after move to be more specific. We don't have use after move in Rust. It's a C++ and C specific feature. So what you need to do here is simply to remember that progress bars are reference counted and clone this progress bar here. So you send another reference to whatever code needs it, and then your program will work as intended. Are there any other questions? If not, I think we can end it early, and then either Nabil takes over a bit earlier than expected, or you continue the practical, but I think you prefer this option, right? So, Nabil, floor is yours.